And so we will develop some basic structure, the Green's function, okay, to derive this structure. And all the main keys is how to implement the concept of conservation law and the nonlinearity of the macroscopic fluid mechanics to derive the stability of the Boltzmann shape. It means that the Green's function of the Boltzmann equation linearized around this profile. Okay, so and when we want to study such problem, okay, then there is some classical problem. Is a Riemann problem. So that the Riemann problem is that the gas it put some separate by membranes. Okay, this in the setting for the Euler equation. And this same setting should also valid as initial data is also valid for Navier-Stokes equation, Boltzmann equation, because when you separate them, then they here are two equilibrium states. Okay, then you can put them as your initial data. This both are for the fluid mechanics and the Boltzmann equation. Okay, and the structure, okay, in the label of the Euler equation, okay, then the possible pattern is a shock wave, a reflection wave, okay, some contact. This is a picture for the Euler equation, okay. Then everything just here is just a line, and here just a straight line, and here this expansion fan, and we expect, okay, and this picture should be valid for viscous flow like. Okay, artificial viscosity, Navier-Stokes equation, okay, and also the Boltzmann equation. This picture should be true, but on the low viscous problem, no one ever, okay, such pattern haven't established yet. Okay, so to study such problem, okay, you might need to have try to study some simple problem. Okay, say for example, just look at the stability of this component. Can we derive the stability theorem on such components? Okay, or can derive some structure of the both on the label or on this label. Okay, and now you have something in your mind. Though. You want to develop a tool. Okay, so now the question is to develop a tool. Okay, eventually it will help you to establish the wave pattern. Okay, and their interaction between those three components together. Okay, so you not only to get just only the theorem. You need to get some qualitative structure about wave propagating around the shock or reflection or contact or reflection. You need to know how those objects that interact each other through this acoustic wave. Okay, so that you need to have some detailed structure of the solution. Okay, so we're starting from look on this problem first. Okay, so to derive the structure or solution, to derive a solution with wave propagating structure. Okay, so now let's just go back to some basic terms about what the Boltzmann shape profile. Okay, so the Boltzmann shape profile. So here this study is look at the case that the shape profile is stationary. Okay, because it just take some Galilean translation. Okay, any traveling wave can become a stationary solution. Okay, so by some suitable Galilean translation, okay, then the Boltzmann shape profile can be related to a stationary Boltzmann shape profile. Okay, and now in here, this two far field is equilibrium state. The equilibrium state is a form of Gauss. Okay, so this is a function in the velocity field. Okay, so here the Kc. So in here, this phi is a function of two variables, x and the Kc. Okay, and x is one dimension, and the Kc variable is three dimension. Okay, so this m is Maxwellian. Okay, this is like a Gaussian. Okay, in the velocity distribution. Okay, so Kc1, Kc2, Kc3. This means the molecular velocity. Okay, and here this law theta u. Okay, v is the density velocity. Okay, so this one it can relate at the temperature. Okay, so now this state is equilibrium state for the Boltzmann equation, and And now, since that we are talking about the shock wave, okay, so this means the end state is a stationary solution. So this is a Raykan-Hugoniot condition. Okay. So and the shock profile show, okay, if you let these two end states, okay, so here these two end states are close to each other, and then the profile, okay, will look like an hypertangent profile. Okay, and the existence, okay, and the existence of a Boltzmann shock profile, it was obtained by Karl-Fishnik-Krenko, okay, for the hard sphere model and hard potential model, okay, and recently done by Taiping and myself, okay, we introduced the center manifold could get another proof, and the main purpose is that this new approach, I mean, tell you that in the structure of the Boltzmann in the structure. So in here, this U, okay, there's a function in the macroscopic in the full variable, okay. And now if you project this phi into its macroscopic components, okay, then one can show you that on the level of fluid mechanics, okay, the Boltzmann shock profile is monotone, okay, in the density, velocity, and the momentum, okay. So that in this new approach, okay, and the motivation, okay, the motivation we study the stability of the Boltzmann shock profile is we want to prove that the solution of the Boltzmann shock profile is a positive valued function. That's our ultimate motivation. Okay, so we name it very narrow-minded because we just want to prove the positive value solution. Okay, so then we just impose some basic property about an evolution equation. So the way we prove the positivity is through two criteria: by stability, okay, regarding to the time, okay, and also the maxima principle of the Boltzmann equation as a time evolution equation. If you choose the initial data is a positive valued function, okay, and the Boltzmann equation is a physical problem, okay, you can write it in two parts, gain part and lower part, okay, then there is a maxima principle. So then the maxima principle will tell you if your initial data is a positive valued function, and then the solution will remain as a positive valued function. Okay, that's one thing, the maxima principle. And the other thing about that, if your initial data, the difference of your initial data and the Boltzmann shock profile, if their macroscopic component is 0, okay, the total macroscopic component is 0, okay, then you can apply energy estimate to prove the stability. Okay, so now with this stability property and maxima principle, okay, then eventually you can prove that the Boltzmann shock profile is a positive valued function. Okay, so this is our original the very original motivation to study the shock stability or shock profile. Okay, but now when we come to this level to the interaction of the shock and the other pattern, so we need to look something else, which is also stability, but we need to remove such condition. This is too strong. I mean, if you consider in terms of Riemann problem, okay, and then the difference of the total mass and the Boltzmann shock profile, the macroscopic component, this condition may not be hot. Okay, so we need to have some preparation. Okay, and then now let me, but the proof, okay, the proof in the stability theorem is very useful. Okay, so so we need to have some, it will pave some way for the future study. Okay, so now let me give you some review about the stability of a shock profile. Okay, in terms of energy estimate. Okay, so then so now you think in terms of the Navier-Stokes equation. Now we switch our mind, okay, to the Navier-Stokes equation. Okay, and then And now if we assume your initial data is a perturbation. Okay, so this initial data is a perturbation of this viscous sharp profile. Okay, and then there is methodology introduced by Goodman. Okay, if in the case this viscosity coefficient is identity metric, and the total mass of the perturbation is 0. Okay, and then also want to assume that the initial perturbation is small in the sum superlap norm. Okay, and then one can prove the stability. Okay, and the proof. Okay, so now let me just tell you what is the essential in the proof. Okay, the proof is a conservation law. That the conservation law is in the I. So now if you rewrite the perturbation is in the conservative form. Okay, and then you can derive the conservation law. So this means that. So this gives you the conservation law. So this means that if your total mass in the initial data is 0, then the total mass remains 0 for all time. Okay. So with this concept, okay, then you got a basic property. Then you can introduce a anti-dilutive variable. Okay. Why we need to introduce this anti-dilutive variable? That means if you look at this linear part of the equation, okay. If you look at this linear part equation, the derivative of sharp profile is a solution. Okay, so this means that this linearized equation has a 0 eigenvalue in the operator. So in order to take out this 0 eigenvalue, one introduce this anti-dilutive variable, and there is the Nishihara, Matsumura. Okay, they also introduced the same notion as anti-dilutive variable to study the viscous conservation law. Okay, so with this anti-dilutive variable, then this equation here, it becomes in this form. It becomes in the convection form. Okay, so in here this divergence form, then there is a 0 eigenvalue. But when you switch to this convection form, then the 0 eigenvalue is gone. So you already factor out the 0 eigenvalue mode. So then you use one more property around the sharp profile. Okay. So now here this sharp wave is the compressibility. Okay. So on the field of the sharp profile, that the eigenvalue is the derivative is negative, so you got some compressibility. So that means you can just using integration by parts, you can get such energy estimate. So this proves the stability. Okay, and now what is the advantage and the disadvantage? Okay, the advantage here is it gives you the global, estimate of the solution for all time. Okay, but the disadvantage is that it do not tell you the structure of the solution, how fast it decays to 0, and where it's big and small, it don't tell you. So this the disadvantage of the energy estimate. Okay. Now let's okay. So then they and the other approach, okay, to study the stability problem. Okay, so if we want to rewrite the equation of the anti-dilutive variable, okay, then and the Taipei Yu, okay, introduce the approximate Green function, okay, and the Green function give you a lot of details and information about the solution, and then it tell you eventually how the structure of the solution propagate out. Okay, so with a very localized structure in the space and time variable. Okay. So this, the Green function was introduced. Okay. Now let's have some. Okay. So now let's switch to something very philosophical. Okay, about the structure of the solution. Okay. So I mean, so in the low stability of the sharp profile, there is some structure which called the local structure and the global structure. Okay. So what is the local structure? That means if you put some small perturbation, okay, around the data, okay, so there is some wave structure go out, okay, and then this just hollow structure. It just exists some moment in space and time, and it's in the transit. So here, so the 1, 2 wave go out. This is a local structure, okay. And now how about the global structure? For the wave, it it will suck into the shock wave. Okay, then it stay there global in time. Okay, so then so you see for the wave propagation in the around shock point, you have two patterns. So this is local. So all the property here 1, 2 means it's only local in the space and time. Okay, and then around the shock is a global, or the structure remains a similar structure global in time. Okay, so now we want to devise some analysis. Okay, it can tell you this local structure and this global structure simultaneously. Yeah, because it's the global is only around the shock. Okay, I mean global in time it stay there for all time, and the local just means it's go there just okay, just like when you listen to my voice, it just pass through your ear here in and here out only in a given time.
Global with respect to
time around I say local and global regarding a time. Okay, so every information propagate to the time, then it become global, exist in all the time. Stay in the suck, stay in here.
I know it's local, global with respect to time, but also with respect to space around the shock.
Yeah, that's right. It's localized in space, but global in time. Okay, but for this one is local in both space and time. Okay, so you need to distinguish some different physical characteristic. Okay. Now I'm switched to another pattern. Okay, because the reason I switched back to here. Okay, I want to emphasize on this global structure. Okay, global structure in time. Okay, though I mentioned that the energy estimate. Okay, in the Goodman's proof. Okay, do not give you some good rate of convergence. Okay, but however, because the Goodman he did it for the system. Okay, so it cannot have a rate of convergence, exponential convergence. But if it's narrow-minded, look at the scalar equation. Okay, so like look at this linearized Berger equation. Okay, and then we know that when you linearize the Berger equation, you have a Kohlhoff transformation. Okay, eventually this problem can be reduced into a heat equation. Okay, with some low order term here, and then from this Kohlhoff transformation, you realize the solution decay in time exponentially. Okay, by Kohlhoff transformation, you realize. Okay, now we try to interpret what is behind the Kohlhoff transformation. Everything comes with a reason. So okay, now you want to know the reason. Okay, so the reason you can think in this way. Okay, so now here this okay, so you look here. This is shock profile. So what do we mean the shock profile in terms of entropy condition? So this means the entropy condition in shock wave. This means that say this is a shock. Okay, this is position of shock, and all the characteristic curve propagate in this direction toward the shock. This entropy condition from the conservation law. Okay, and now we think. Okay, now look here. This is the Euler part. The Euler part means the wave will propagate. The answers will propagate toward the center. This one will propagate toward the center. Okay, this is basic structure. If you look at this part of the equation. Okay, and now how this wave propagation of the shock can realize in terms of energy estimate. So now you look here. So you put so here the basic line of Kohlhoff transformation. Okay, this means you multiply some weighted hypercosine function. So you can realize this one as a weighted function like this one. So now turns out you look at the weighted energy of. Okay, so you take this as the weighted norm. Okay, and then multiply with the answers. Okay, and then you compute the L2 norm. Okay, so now though the answer itself do not change the shape very much, but the position of this answer going toward the interior. Okay, but your weighted function is exponentially decay. So it turns out that your weighted norm is exponentially decay. Okay, so this means that by if all the way go into the shock, okay, then the energy estimate is quite good. Okay, it gives you the rate in the same time, because you're in here you have this weighted function. This weighted function means all the information is localized. So this means your solution should be decay in the space and time, because this weighted function. So this means when you have when all the way going to the shock, okay, energy estimate give you decay in the space and the time simultaneously. Okay, so that but under the condition, all the way go into the shock. Okay, but this condition, all the way go to shock, is a very strong condition. It's too strong, because look here, if you look at the wave propagation in the hyperbolic equation, you see some way going to the shock, but some other way do not go into the shock. Some other way is just crossing it. Okay, so this means, okay, so this wave pattern tell you, okay, if you just using the standard, okay, this weighted energy estimate don't work. Okay, so now you need to try to think, okay, how are you going to separate that wave toward the shock and the wave just pass by. Okay, so you need to understand how to separate these two family. Okay. Okay. So the way, okay, so now the way to separate all those scale is based on the decomposition. So now before if we do the PD in general, we decompose the solution in terms of variable. Okay. So we're using the eigenvectors and eigenvalue of the Euler equation to decompose the solution right at the coordinate system. Okay, and now we use a different concept. We decompose solution regarding space and time. Okay, we use the structure to decompose the solution. Okay, so now we see these things will go in this direction. We try to separate them. Okay, so now how to separate this? Okay, so we need to refer to the basic wave propagation in the hyperbolic equation. So now we just look on the label of the Euler equation, linear line around the shock. Okay, so now if I put some initial data, okay, as a delta function in here, okay, and with some vector, okay, and then eventually, okay, you think this is a pulse. Okay, under this around a shock, okay, and then eventually you will see the pulse will decompose. So now if we decompose the initial data just regarding to this form, okay. So here this R1, here this 1 and 2 is means that the eigenvectors for the Euler equation linearize around this constant state, okay. And now here this way the vector is corresponding to the shock, the difference of the shock. Okay, so now if you decompose your initial data regarding to this hyperbolic picture, okay, and then eventually the pulse, it will separate into these two parts. Okay, this 1, 2 is just go into this direction, and there is some component left, okay, or disappear, okay, or hide within the shock layer. Okay, so now these two, the vector here and the vector here, give you the idea how you're going to separate the structure. Okay, so now you will see. Okay, so now you think this part is a transient part. Okay, it's a transverse to the shock. Okay, and now you can read this part as a compressed component of a shock. Okay, because it just tell you the difference of a shock. Okay, so now how I'm going. Yeah.
Suppose you have information to the right of a t-axis, then your decomposition with respect to U minus will not be so. Yeah, suppose.
Then you need to add some extra, because I'm only look at the Boltzmann equation. Okay, for the Boltzmann equation, shock either in 1 or 3. Okay, but if you want to look at general, okay, then put others in here. Okay. Okay, so now I'm going to implement this structure, okay, to the Boltzmann equation. So now here, this one is a linearized Boltzmann equation around the shock profile. Okay, and so So now I'm going to take care of the macroscopic component, okay, because the macroscopic component of the Boltzmann equation is the thing related to the Euler equation, okay. So we decompose the macroscopic component into three parts, okay, into two parts. The macroscopic component it means R1, R2 is of course is a component. Okay, 1 and 2 is corresponding to this macroscopic component, okay, and here these three, okay, this macroscopic component related to the shock. Okay, the difference in the shock. Okay, so first it take care the macroscopic component. It just uniformly decompose into this T part, transverse part, and C is a compressed part. And then okay, it leave the microscopic component there. Okay, and now with this decomposition, okay, then we try to devise construct some apparatus to construct wave propagation. Okay, so first we take it. So I define the T operator. Okay, T operator means the transverse operator. What it means? Okay, so this means I just try low R problem. Okay, low R problem is to solve the original problem. Okay, but it's too much. We try to reduce the so now okay. Okay, so let's see here. Okay, so now we just look. Okay, if we try to solve this linear line equation, okay, with zero initial data with some input term here. Okay, so now here I just put because every initial data initial value problem can be converted into inhomogeneous term with zero initial data. Okay, so now we just look how we solve the initial. Zero initial data, but with input term. Okay. Okay. So now here, say I have okay. So here, say this the input term of our original problem of the control problem of the Boltzmann equation. Okay. So first, we are not trying to solve the whole problem first. We just try to solve the problem on the transversal part component. Okay. So now let's define this T is some operator. Okay, you just try to solve the problem on the transversal component. So then this problem is reduced into an OD, a PD, or two-dimensional only. Okay, and now you have some requirements. Okay, because this when you try to solve in this on two components. Okay, that means it do not solve the original problem. It just solve part of the solution. So you might have a truncation error. Okay, so now you need to ensure that your truncation error. Okay, you need to make sure this is your approximate solution and plug into the original problem. Okay, you need to make sure your truncation error is exponential decay in the space in the space variable. So in here, okay, so that means I put the weighted function. Okay. So now if this remains finite, this means your truncation error is confined around the shock layer. Okay. And now and then the procedure to construct it's very simple. Is that first it's just some iteration scheme. Okay. So now you just look at your input term. You just look at their transverse component. Okay. And then you just try to solve this with this input term, okay, and it takes a semi-group with a constant state. So this U plus minus is the green function at the far field, okay. So now you try to solve the solution regarding the green function at the far field, okay, and then you just take this partition of units, okay, and then you sum it together as the approximate solution, and then this approximate solution is accurate because the green function is a far field, so this is accurate at the far field. Okay, and it also give you when you plug in the solution into the truncation error. Okay, so you plug in this one into the equation, you got the new truncation error, and this truncation error is always decay in the space and time exponentially. Okay, and now the iteration is doing that this one. Okay, so you put here this. So here this is your iteration. So every time with this plug in here is just a transverse component. You plug in here, you got the whole arrow. But when you plug into the origin, the iteration, you only take care of the transverse part. Okay. So this one will guarantee you to satisfy this condition. Okay. But when you're doing this one, you sacrifice this because you only take care on the transverse part. So you sacrifice some information on the shark front. Okay. So this means so the information lost the shark front. You can think this is interaction of the far field and the shark layer. Okay. So every time.
So information lost on the shark wave, and that is interaction of shark with the far field.
Right.
This information you make sure is localized.
Yeah.
It is the truncation error of it.
Yeah. So this one. So this exponential decay. Make sure everything localized around the shark. Every time you do the iteration, all the error is just confined in around the shark layer. Okay. And okay, so now you also need to take care. Okay, I mean, so though this compressed component is information lost in the shark front, so you count this one as a local wave front tracing. So use this arrow. Okay, then you obtain the dynamics of the shark front. Okay, so eventually you use the TR operator and this local dynamics. Okay, and then you use it as a basic approximation. Okay, so then you take this T and this D. Okay, and plug into the equation. Okay, and then this one is a total error. Okay, and then now because this y is and now this total error because you already take care of the shark front and the interaction. So then this y actually contains nothing. Okay, I mean nothing in what sense? In the macroscopic component, because all the transverse wave is gone, and the shark front translation shark front already taken here. Everything is gone. The only thing left here is essentially the microscopic component. Okay. And now when you reach to the microscopic components, what you need to do, okay, you need to estimate. Okay, you need to estimate this one. Okay, now take this one as input term to your original problem. You want to look at the response to the original linear problem around the shark profile. Okay, but now in here we need to switch our mind. Okay, because now this one already is passive, essentially nothing. Okay, so it can get some good thing on it. Okay. So what you want to get a good thing here, okay. So now what you need to do is you need to try to solve this problem. Okay, I mean this is regarding, so this one you can take this C and respond to this problem. Okay, but for this one you have a very good tool to deal it. Okay, so what is the tool? The tool is that we don't try to solve it, we try to approximate it. Okay, so the idea is that okay, you just take this one as input term here. Okay, and then you just give an extra damping. Okay, so now I'm going to tell you this extra damping is good. Why? Because this damping only applies on the 1 and 2 component. Okay, 1 and 2 component. And now look here, initial data is 0, and this one contains nothing. Okay, so to this problem, actually the 1, 2 component is nothing, almost nothing. So okay, so then this means you can think this one is just virtual. Okay, you can think this one is virtual. Okay, regarding the 1 and 2 components, and now here you also have a small parameter epsilon. Okay, but now this small epsilon play a very good tool. What? Because this one is damping, so this means you're damping on the 1 and the 2 component. Okay, so now okay, wait a minute. So here, okay, so now here look at this picture. Once you damping and one, okay, so this is the whole picture of the original problem. Okay. But so that means you have 1 way and the 2 way go through here, okay, and you have 3 way. But if you apply damping on the 1, 2, that means that the area information carries through 1 and the 2 will decay exponentially. So this means so effectively structure of this problem only the 3 way left. Okay, so only on the compressive way left. And now I just tell you before, if all the way, I mean essentially all the way is toward the shark, energy estimate is very good. Okay, so for this damping system, this G is a damping system. Okay, then it's everything compare is move toward the shark. Okay, so It's also so it allow you to find some global exponential growth weighted function. Okay, and then you can do it, and then you can solve this C by energy estimate. Okay, then you got this, and then this C you got the global. Okay, so then this one you got the global estimate. Okay, and the solution decay exponentially in space. Okay, and now in here this one is, I mean, your error is exponential decay in time. So it turns out this C component is decay in the space and time exponentially. Okay, so now this one tell you construct a C operator to come to approximate ways around the shock. Okay, so now you got the O component to construct a solution around the shock or the component away from the shock. Okay, so we define. Okay, now in here, okay, here you got this global energy estimates. Okay, and then using the green function, okay, around the constant state, and then you can convert the L2 estimate into the pointwise estimate. Okay, so now you got the structure of the solution pointwise. Okay, so now you are ready to define a TC scheme. Okay, so the TC scheme that, okay, using this T, okay, I just T operator and the D local wave fluctuation, and now you sacrifice something. So now this one is, so this one you also have a global structure pointwise. Okay, so now use this one as approximation. Okay, and then take this approximation. You got the truncation error here. Okay, and now the point is that in this truncation error is only on the 1-2 component. Okay, only on 1-2 component, and here you have small epsilon. Okay, so this means, so then use this T and this R. Okay, it define a converge. It define a series. Okay, and then you can prove. Okay, and then this actually is quite a big job. Okay, to prove the convergence of this series. Okay, and as a truncation error. Okay. And now all those truncation error is decay in the space and time. Okay, so I just skip here. Okay, it's eventually you will get I just go to conclusion. Okay, eventually you can find out that if I have initial value problem like this one. Okay, so all the initial data is confined around the shock. Okay, and then you will see the structure is of the solution essentially like some heat kernel. Okay, and here there is some interaction between the heat kernel and the shock layer. Okay, but everything in here still exponential decay in the space and time. Okay, and now with this very refined information, then you can get this kind of scattering pattern of wave propagation, and then this is good enough for you to obtain the stability of nonlinear problem. Okay, so I just tell you. Okay, then the problem is done. Thank you.
Do you have questions or comments?
You have the scalar equation.
Yes.
And the energy method, but that